Okay, and it's exactly 11:30, so I think we'll go ahead and get started. Good morning and welcome everybody to this very special edition, Reading Week edition actually, of Trainee Talks. Trainee Talks is a monthly webinar series showcasing the research topics of our CREATE graduate students in their area of interest related to software engineering and AI. My name is Lori Akiyama, and I'm the program coordinator for CREATE SE for AI here at Concordia University, and I'll be moderating the webinar today. Today, we are very pleased to have two of our program trainees, Pierre-Olivier Côté and Akalanka Galappaththi, joining us to deliver their talks. Sorry if I'm distracted, I'm admitting people as they, as they enter the waiting room here. Pierre-Olivier Côté is a master's student in software engineering at École Polytechnique under Professor Futscom. Pierre-Olivier is always looking for better ways to ensure the quality of AI products throughout their life cycle. And today he will be speaking about quality issues in machine learning software systems. Immediately following, we will hear from Akalanka Galappaththi, who is a PhD student at the University of Alberta under Professor Sarah Nadi, who will be presenting his current work on a data set of generalizable Python code change patterns. This webinar is being recorded and will be available to view on our CREATE website at se4ai.org and also on our YouTube channel. So I think everybody knows our usual procedures, but I'll ask that you please keep yourselves on mute until we get to the Q&A session at the end of each speaker's presentation. And then you can raise your hand in the chat to ask whatever questions you have for the speakers. So with that, I'd like to turn things over to Pierre-Olivier to begin his talk.
All right, thank you, Laurie. So hi, everyone. I'm glad to see so many people here to attend our talk. So as you know, today I will be presenting one of my the research project I've been working on in the past few months with some of my peers. One of them, maybe you know him, it's Rashad. I'm not sure, maybe he's in the talk, but yeah. So let's get started. So the goal of this research project is to develop a catalog of quality issues in machine learning software system. So now you might ask,
Pierre-Olivier, are you, sorry to interrupt, but are you going to be sharing your screen?
Oh, thanks.
Thanks. Thank you.
Now you can see it, right? Super.
Yes.
Okay, so it will go better this way. So the goal is to develop a catalog of quality issues in machine learning software system. Like I said, let me explain what is a quality issue and what is a machine learning software system. So the quality issue is an issue with quality, right? So that part is obvious, but maybe you're asking yourself, what is quality? And the best way to describe it is with an example, I think. So let's say you have two systems that both of them are functional, and one is better than the other. The one that is worse probably has some quality issues. And a machine learning software system is just any software system with a machine learning component in it. So yeah, we try to develop a catalog of quality issues in machine learning software system. And we think the best way to achieve that is by interviewing practitioners because they have first-hand experience. By practitioner, I mean software engineers, project manager, ML engineer, data scientist, and yada yada. So here's a quick diagram that summarizes what we did and what we plan to do. At first, obviously, we try to recruit people. So we search for a practitioner, we got their email, we send an invitation, then we conducted an interview of about 45 minutes. And in total, we conducted around 42 interviews. Then the next part is to extract quality issues from the discussion we've had with the practitioners. So to do that, first you transform the audio file of your interview into a text file, and then you do coding. So just to explain it really quickly, you try to find quality issue in the discussion you had with the practitioners by simply tagging some part of the speech, some part of the transcript, and you assign it to a quality issue. And 2% were doing that, and so you have two different versions. And the goal in the end is to merge them together. So there was a third person who was a moderator and resolve conflict between two versions to have the final version from which you will be able to extract codes. So yeah, when we have the final version, as I said, we do result analysis, and hopefully we do have some findings that I'm going to present to you today. Keep in mind that I finished the result analysis, but not all of my team members. So currently, like there's still work that need to be done for everything to be clear and concise and peer reviewed. But hopefully, what I will share with you today will be useful and interesting for you. So yeah, and at the end, obviously, we're gonna validate our finding with practitioner. We're gonna send a questionnaire and ask them if they ever had the quality issues we have encountered. And with the results of the questionnaire, we will be able to have a more quantitative approach. Right now, it's more qualitative. So yeah, let's get started. So the goal of this presentation is I will just try to summarize what are the most interesting findings that we've seen. And to do it in the structured way, I will address each quality aspect that have been mentioned in our interview, and maybe mention the most interesting findings once again. As you can see, there is a lot of quality aspects that have been discussed during the interview. So we will try to, well, obviously we won't have time to cover the last one, but the first one, hopefully, we'll try to cover them. All right, so let's start with the first one, reliability. As you already know, a model is strongly coupled with the data it has been trained with. And any issue with the data might result in a change in performance or accuracy in the end model. So I guess you're not really surprised if I tell you that most reliability issues we've seen were caused by data. And to be exhaustive, we'll check the life cycle of data and see what kind of issue can happen at each one of these phases. So at first, you have a process, right, that you try to model that may happen in the real life. And then somehow you collect data by observing this process. This is a data collection phase. Then you do data preprocessing. So the data you have collected can be ingested by your model, so the model can make prediction. And then the model make a prediction. And like I said, in each one of these phases, you may have quality issues. So in the process phase, there's some issues I think you are most likely already aware. That is data drift and concept drift. Data drift is when you have a change in the distribution of the features, and concept drift is a change in the relation between the features and the label. And a common solution to that is to automatically retrain your model. So this is what practitioners tell us when it's fairly common. They say that they do this to address that problem. However, this is not always enough. Because let's say you have concept drift and all of your features become meaningless to predict the target variable, then your model performance is going to be decreased over time. And with automatic retraining, it's not going to be enough to combat the drift. Similarly, if you have a big change in your data, such as COVID, this has been mentioned a few times, all of your data prior to COVID is not really useful anymore for your task because everything has changed all of a sudden. And so during a short period of time, your model are going to be really not useless, but really bad, and there's not really something you can do about it because you do not have enough training data to achieve the same performance you had in the past. Now for data collection, something we've seen is annotation drift. That is the way that data is collected changes over time. It's pretty similar to data and concept drift. The difference is it's during when you collect the data, and to clearly make the difference between data drift, concept drift, and what happens in data collection, we say annotation drift. And generally that happens when you do not have a standard way to collect data. It changes over time. So as a solution to that, you can simply define an annotation standard. This is what is done, and that's pretty much it. And now in the last phase, data preprocessing. So now you have collected data from the process. Now you have to transform the data in a format that is ingestible by the model. There's two kinds of issues. The one is that the data pipeline are sometimes brittle. They crash on unexpected input, or the preprocessing is seeing an outlier instance, and so the preprocessing is really bad. So yeah, more general problems. Something that came up often during our interviews regarding reliability is that having external data providers can be, it's always a challenge. The reason is these data providers don't know that their consumers are ML models. And as such, they don't design their system to be reliable enough to be used by a model. I think the code right there summarizes it pretty well. And the two types of issue we've had is we've seen that the most common one are availability issue or data inconsistency, consistency issues. So the first one is pretty obvious, self-explanatory. When you try to request the data to make a prediction, it's not there. Or maybe even for training, the data is not available. For data consistency, this is a bit more interesting. This is for the same record that you're trying to fetch at different time, you will get different values. This may happen if you have a change of units, but also in sometimes if the data provider decide really explicitly to change the historical data. And I have an example for that. One of our practitioners were consuming from a weather API. And I think the weather API, the person providing the weather data had a faulty sensor. And as a result of this, when they discovered they had a faulty sensor, they correct all of their historical data with that sensor. And this is a big problem when you have an ML system, because first, your model is trained on some distribution of data, and all of a sudden it has changed. But second, in their case, it was not mentioned, it just happened. So all of a sudden, your model performed poorly and you do not understand why. And when you try to understand why, you do not have the data to reproduce the bug. So anyway, yeah, I'll get to that later on. All right, so yeah, just like I mentioned, debug. So we covered reliability a lot. We'll move on to the other, and since we do not have we still have a bit of time. I'll try to go fast over the next quality aspect. So debuggability. Debugging an ML system is difficult. Like I mentioned, when you have unstable data source, it's really difficult to debug anything. Because to debug, you have to reproduce a bug. Generally, that's a common procedure. You try to reproduce a bug. And to do that, you need to have the data that triggered the bug. But if you're not able to have this data, well, you cannot reproduce a bug, right? And as a result, what we've seen happen in some cases is that when the practitioner is not able to reproduce a bug, they simply ignore it. So you have bugs that are not necessarily fixed. And that is a problem, obviously. Another aspect is like organizational challenges. So let me give you an example. Let's say you work in a big company, and your machine learning software system consumes data from other data providers internal to the company. And these data sources are handled by different teams. And I just said it, most reliability issues are caused by issues with the data. So most of the time when you try to debug your system, you will end up inspecting your data source. And since these data sources are managed by other teams, this process of debugging your MLS becomes really long, because debugging your MLS is not necessarily the priority of the other teams. So a lot of back and forth, a lot of waste of time. Right? So that's it for debuggability. Let's move on to explainability. As you already know, trying to explain the prediction of a non-interpretable model is not easy. And there are tools that try to explain the prediction, but it's not perfect yet, right? And what we have observed is that the tools they do not provide good explanation for the user of your ML system because they are too technical. And as a result, these tools are mostly used by the practitioner to debug their system. But even then, the explanation, it's not reliable. The explanation that are given by the tool, yes, they are correct. I mean, they're not worse. But the thing is, it's difficult sometimes to understand for a practitioner. And so it's not reliable in the way that maybe you do not get the information you want every time. And if we have time, maybe I'll go deeper in that. So moving on to maintainability, we've heard a lot that there still is poor dataset and model documentation. This obviously can be a problem if you are inheriting the project of another team, and you don't know how the model has been trained. Well, maintaining is going to be a big problem. And we've heard some cases that they had to start from scratch a project because they didn't know how it was trained. Something else that is not specific to machine learning is that managing dependencies is still difficult. And I mean, there's some open source ML libraries that change a lot of versions. So in that way, maybe it's related to ML, but yeah. So we talk about maintainability. Now let's move on to efficiency. Something that everyone knows is that training a model, at least a large model, is expensive. And at inference time, the efficiency issues we've heard is latency issues. So it takes time before you get an answer from your MLS. And the other one is memory consumption. Memory consumption, obviously, is when you use large model, it consumes a lot of memory. So this sometimes can be a challenge if you have constraints. Latency issues, that's interesting. Most of them can be solved by working on the data preprocessing pipeline, not on the model. So for example, a trivial example, you should use a vectorized operation instead of for loops, right? So most latency issues comes from the data preprocessing pipeline. All right, we're almost finished on time. So the last one, maybe evaluability is that, anyway. The last one is that evaluating the quality of a model or measuring the quality, not of a model, but an ML system in general, is difficult. First, the ML metrics that we use to evaluate the models on offline manner are not always a good proxy of the quality of your ML system. So you might have an improvement in your model, but in the end, it's not any better for the usage of the ML system. And as a result, what most practitioners do is to define proxy metrics, or they use business metrics, and they evaluate it in an online manner. So when your product is deployed. But even then, defining good proxy metrics is difficult. So, yeah. And that's the last point I'm going to mention for today. Another thing related to evaluability is that defining an acceptance criteria with stakeholders is difficult. They do not have any ML knowledge, so you cannot say we'll reach 80 accuracy and we are happy. That's not how it works. Most of the time, what we have observed, at least, is an iterative process with the stakeholder, and basically the stakeholder define somewhat of a test set, and the stakeholder observes what are like for the samples that are failing to be predicted, for the errors basically of their model. The stakeholder looks at them and decides whether it is acceptable or not that the model makes an error on that. And this is an iterative process that we have seen to be used instead of defining like an acceptance criteria specific acceptance criteria. All right. So I've presented the research project, every step of it. Then I've covered reliability issue in great details. Then I've covered other type of issues, but more less in details, right? So that's all for today. Do you have any questions?
Thank you very much, Pierre-Olivier. I think that's a great presentation and a good screen to leave up as we start the Q&A. I see that Jasmine has raised her hand. So Jasmine, go ahead and ask your question.
Hi, Pierre-Olivier. Thank you so much for your nice presentation. So you briefly discussed one of the challenges was maintaining dependencies, and I was just curious if in your interviews you asked the practitioners about their practices in managing those dependencies, and if you've noticed if there was any difference between the frequency of updating dependencies in machine learning projects versus traditional projects. So is there a big difference, and what are the major challenges related to managing dependencies?
Yeah, I guess the first part is how they address these challenges. So generally what they do is they, well, an obvious version is they fix the dependent, like they say, this is a version of the library we are going to be using. And the list of dependencies is like reviewed like code. So if you ever try to make a change in the dependencies where, well, you have to justify it and talk with your peers and make sure that it breaks nothing. Can you remind me what is the second part of your question?
Yeah, I was just wondering if you've noticed a difference between the frequency of updates and dependencies in machine learning projects versus traditional projects. So do machine learning projects seem to update more frequently or less frequently because they're so sensitive to changes?
Yeah, I'm not aware if like what is the frequency in normal projects. So I'm not sure if I'm going to be able to give you a good answer, but there are some open source, well, there are some ML libraries like the transformer, it has been mentioned, that add a lot of changes throughout time. So if you do not fix the version, well, it's going to automatically update, and maybe it's going to break something in your pipeline. So,
Thank you. Thank you.
No problem.
Thank you, Jasmine. Khaled, go ahead with your question.
All right. Okay, so first of all, thank you so much for the presentation, Pierre. Always interesting stuff. I was wondering whether the practitioners mentioned how they measured like the different quality aspects of their project. So was it like their intuition of how the thing is going or their personal experience, or did they have tools to measure like reliability or, you know, some other aspects of quality?
Yeah, no, they did not have any tool. Yeah.
Just interesting.
And yeah, what the evaluability challenge is really if your MLS is doing great at the task it's supposed to do. So that's yeah.
Okay, no problem. Thank you.
Thanks, Khaled. Does anyone else have any other questions about Pierre-Olivier's presentation before we move on to Akalanka?
I have a question, if I may.
Yes, please, Tanya.
Yeah. Hi, Pierre-Olivier. Good to see you again. Thanks for the great presentation. I have actually two short questions. So one would be, can you tell us a little bit more about the interview participants and the recruitment process, and a little bit more describing who were the interview participants, also with regards to maybe thinking of diversity or something like that. And the second question would be the organizational challenges. So I would be interested in learning more about what organizational challenges the interview participants mentioned and what would be your response, how to solve these organizational challenges. If you could expand on that, I would be very grateful. Thank you.
Yeah, sure, absolutely. So for the recruitment, we've started with so the research project is done with a company, so Move AI, and we've interviewed first their employees. Then we've looked outside of MoveAI, and we've tried to basically we search email addresses from like GitHub, for example, and yeah, that's pretty much it. I have a slide on that, but I suppose what you want to ask is more related to yeah, but if you want, like I will show it to you actually. So yeah, this is where we fetch participants. So we try Reddit, Slack, Discord, Stack Overflow, both two versions of Q&A websites, personal contacts, GitHubs. So really, we got people from a lot of different countries from what we've interviewed. Is there any? Yeah, we had people from Africa, we had people from Europe, from Asia, from North America, obviously, South America. So in this way, I think it's everyone in the world, but yeah. And your second question is regarding organizational challenges. What I meant to say in this is really regarding debugging MLS system. What I meant by organizational challenge is that do not prioritize your bug when you have one, if you're building a machine learning software system. So this is what I meant, mostly, not something related to fairness or anything like that. Yeah.
Thank you.
Okay, thank you so much. Any final comments for Pierre-Olivier or questions? We have about a minute or two if anyone wants to ask something else. If not, I will thank him very much for a great presentation. Thank you, Pierre-Olivier. And with that, we'll move on to Akalanka. So Akalanka, please go ahead and share your screen. And you'll have to unmute yourself as well, Akalanka.
All right. Okay, I hope everybody can see my screen. All right. Good morning, everyone. My name is Akalanka Galappaththi. I'm a PhD student. I'm under the supervision of Professor Nadi at Software Maintenance and Reuse Lab at the University of Alberta. Today, I'm going to talk about a data set that we constructed. It contains generalizable Python code change patterns. Let me start with an example. This is Bob. He's a software engineer. So Bob is tasked to implement some features for a software that they're developing. So he writes some codes and push it to the code base. Then we got Alice. She's an experienced software engineer. So she pulled the code that Bob wrote because her work depends on the piece of code, some of the code that Bob wrote. Then she realized some of the code that Bob just pushed in are not very good or it's suboptimal. So she makes necessary changes, push it back to the code base. So this is a kind of a common thing that happens in when you develop software, right? People make frequent changes. So sometimes they're just to fix bugs, or maybe they want to improve the code or the software by including new features, or maybe just to make the code more readable or concise. So some of these changes that people make to the code could be repetitive. And the repetitiveness of the code could be an indication of doing something a better way. So if we could have a collection of these repetitive changes and identify this is a way of doing something good, this could be used as a basis to create code change recommendations, or maybe even for automatic program repair. So if we have such a data set, and if somebody like Kathy, an intern, come to a company, and when she writes suboptimal code, instead of Alice going through this code manually and fixing them, a tool can either flag Kathy, say, okay, you're doing something wrong, there's a better way of doing this, or maybe it can automatically fix the code for her. Here's an example of a repetitive code change. where in this case, a developer dissolve a for loop that add items to a list with add all API. And when you look at this change, the after version of this change, it's more readable and it's concise. And in some cases, it could be even faster than using the for loop. But there's a long line of history that researchers leverage on repetitive code changes in source code histories to fix bugs, prepare static analysis violations, API migrations, maybe code improvements. And most of this work are based on Java. And one recent work on Python, despite Python being one of the top most used programming languages in 2022. So inspired by the tools available for Java, we wanted to develop a linter that could flag the developers when they write codes, and if we could let them know, okay, there's a better way of writing this code. To do this, we used the dataset developed by Dilhar and others. So that dataset contained code change patterns for Python. So in this particular example, the developer replaces a for loop that add elements to the variable sum with the sum API in NumPy library. So let me give a brief overview how Dilhar and others find such patterns. They mined 1,000 Python project repositories, and they analyze these commits using an automatic mining algorithm. This mining algorithm mined over 28,000 code change patterns, and that's a lot. And nobody really knows whether these are good without really manually investigating them. So what they did, they took a sample of 2,500 patterns by considering 5 different dimensions. So they consider how many instances were involved in a particular pattern. We could call it frequency, and the size of the change pattern, the size times the frequency, and how many developers involved making individual changes or the instances for a pattern, and how many projects where the patterns are extracted from. Then after manually validating these 2,500 patterns, the authors found 561 meaningful code change patterns. Sounds good, right? So we have manually validated code change patterns. So we thought, okay, we could use these patterns to create our linter. But when we manually or carefully analyze these patterns to write our linter, we found that some of the code changes cannot really use as basis for our recommendation system. Here's one of the examples. In this change, the pattern says remove the plot API and introduce the show API. But these are two different, this API does do two different jobs. The plot is basically to draw something, and show is to display all the graph drawn so far. So it doesn't really make sense for us to flag this kind of code and recommend the developers, hey, replace your plot with the show, right? Because that's not a meaningful change. Let's take another example. This change actually makes sense because this change focused on enforcing a type change on a matrix. However, that particular type in 64 is context dependent. So every time when developer use such a code, we can't really ask them to change it to int 64 because depends on the context. Another project may be using a different data type. So these examples suggest that while mining algorithms are really great at discovering previously unknown code change patterns, without manual validation, we cannot really use all these change patterns as basis for code change recommendation. However, this is not a limitations of Dilhar and others, rather it's a very common problem for most of the code change pattern mining algorithms, especially when they're mining these code change patterns on while, because the mining algorithm focused on the syntax changes rather than the semantics. So in all these studies, developers, after mining these patterns, they evaluate a sample manually, then they decide which patterns are actually useful or meaningful and which are not useful. Then they derive their insight based on the useful patterns. So to use code change patterns as basis for developing recommender systems, we need to find generally acceptable patterns. So our goal here is to provide a well-documented guideline to identify generalizable code change patterns. Then after identifying them, if you could find certain characteristics, maybe we could derive a criteria how to automatically identify them instead of manually going through them every time. So here's how we do this. First, we take the 561 patterns that Dilhar and others found, and we took a random sample and went through each instance to identify certain characteristics of them so we could create a coding guideline. Then we apply the coding guideline on remaining patterns so we could annotate which patterns are generalizable, which patterns are not, and if the pattern is a generalizable pattern, what are their characteristics. To identify the code change patterns, first we compare the before and after version of a change, and we see whether these two changes are semantically similar. So otherwise, we would discard them. For example, removing the plot API and including the show API, right? Because it doesn't necessarily make sense. Then, if the change is semantically similar, we see whether we could, how generally applicable the change is. For example, something like this. If the change pattern involved a particular data type that we cannot generally recommend, or if there's an API or attribute that is project specific that probably won't be able to recommend to like other projects, we discard them as well. Additionally, we found certain patterns, code change patterns does not contain enough information to determine when to recommend this code change. So in here, the change pattern involves enclosing this joblib dump API in a context manager. In this particular case, it's the temp file. So every time when a project uses the joblib dump, we cannot really recommend them to use the temp file context manager because who knows, maybe they don't really want to put them in a temporary file, right? It could be they want to keep it as a regular file. So in such case, we discard those patterns as well. So if all of these conditions were satisfied, then we consider a pattern is a generalizable pattern. So before we manually validate these patterns through our coding guideline, we discard the patterns where each instance are changed by a single developer. So the reason is we believe a pattern would be more generally applicable if at least 2 developers find the same change is useful. Then after discarding these 134 patterns, we use the remaining to manually evaluate through our coding guideline. Then we discard 355 patterns because either they are not semantically similar or the pattern is not generally applicable. So the 2 slices, orange and yellow slices, show these patterns. Finally, we found 72 generalizable code change patterns. So let me explain, provide some insights of these change patterns that we found. We found 40 patterns that involved context managers. So the context managers in Python allow to handle files or network resources or switch between CPUs and GPUs when developing neural networks, handle error states, and maybe sometimes manage test contexts. So context managers in Python provide a better way of entering into a context and exiting out of it. For example, when you open a file, you have to remember to close it. But with the context manager, developers do not really need to explicitly close it because context manager does it for them. So using a context manager basically provide a means avoid mishandling resources. We found 13 patterns that dissolve for loops to an efficient API. So in this case, removing this for loop with a sum API. So most of the instances or the patterns that we found involved NumPy library APIs. So these patterns focused about runtime efficiency. We also found 4 patterns that involves replacing an API. So these instances are a little bit different compared to the context manager and the dissolving for loop patterns that we discussed earlier. So I'm going to take 3 different examples to explain them. So in this case, developers replace this expression to calculate the average with NumPy mean. So this improves the runtime efficiency in a little bit, and it's also more readable. Then the second example involves replacing a deprecated API, and this new API happened to be a composite API because it creates batches, and at the same time, it allows the developer to drop the remainder when you cannot split the data set into equal portions. So this is a must when developers moving forward with the newer versions of TensorFlow library. The last one, the developers enclose the output of the reversed API. So when you call reverse in Python, it returns a generator. So to access the items, enclosing the output of the reversed API into a container-like list is kind of required. Otherwise, you have to loop through the generator, calling next API to access element by element. Finally, we found 15 patterns that specifically involved Python-specific language constructs like literals, operators, and comprehensions. The first one is about the in operator. Using in allows developers to write more readable or concise conditional statement. For example, in here, instead of combining 3 different conditional operations using Boolean O, could just use a single operator in. Python has different ways of creating sets, lists, and dictionaries. So either you could call the constructor, or you could simply use the literal. So in this case, instead of calling the set, the developers use the curly brackets to make it a set. So it actually avoids additional lookup when you use literals. So it's more like a Pythonic way, and it's provide a little bit of runtime efficiency as well. Finally, the comprehensions. It's a Python idiom. It's more like a Pythonic way. It also improve the readability. Instead of using a loop to create a dictionary, developers simply could use dictionary comprehensions. So when we look at some of the characteristics of these change patterns, or generalizable change patterns, we found that 9 instances of out of the 72 involved API call or certain construct from a library like TensorFlow, NumPy, Spacy, H5Py, and MPMath. And 2 of these libraries like TensorFlow and the Spacy are specific to machine learning. So we found some of these are interesting, even though the number of instances are a little bit smaller. When we compare the number of developers involved, 80% of the patterns involved 2 to 3 different developers when they make the changes. And want to note that we already discarded the patterns that involved a single developer. So every pattern that we found as generalizable code change patterns either involve 2 to 3 developers or more than that. When we look at the projects, since we didn't really discard any projects before we apply the coding guideline, 74% of the patterns instances found in 2 to 3 different projects, and only 9% of the pattern instances found in a single project. So we so just to recap, repetitive code change just can be useful and can be used as a basis to create code change recommendations or for automatic program repair. However, not all change patterns mined by these algorithms are meaningful. So since this is a problem for automatic mining, code change patterns automatically, our goal is to provide a well-documented guideline how to identify generalizable code change patterns. So by following the coding guidelines that we developed, we managed to filter out non-generalizable patterns. Then we found certain reasons for different change patterns and certain characteristics. And when we identified the certain characteristics, we found certain patterns involved specific machine learning libraries. Some of them are like more frequently used general libraries like NumPy, which probably used in data processing. Oops, supposed to become early. So our data repository can be found in this Figshare dump. I'll take any questions.
Oops. Thank you very much, Akalanka. Khaled, please go ahead.
Yeah, so first of all, thank you so much for the presentation, Akalanka. Always good to see you. I was wondering whether there's a difference in the generalizable code change commits, right? Like commit message. Did you find anything interesting there? Did they describe it more in detail, or did they seem to know what they're doing? Like, do you have any insights from the commit message that would show that the change is more likely to be generalizable?
We didn't analyze the commit messages at all. So we specifically focus on the data dump provided by Dilhar and others. So maybe I should have included a link. So that only involves the changes mined by the algorithm and the individual instances. But yeah, that's actually a good idea, because when I was creating the linters, some cases there are useful commit messages that basically says why the change is necessary. Sometimes it's just a huge stack of changes that companies that basically writes. So, but there may be something to investigate on there. But yeah, good point. But I didn't analyze that at all.
Yeah, thank you so much. And in addition, maybe like I guess commit messages that may mention refactoring are more likely to be generalizable. I guess that's just one thought I have. But thank you so much for the answer.
All right, no problem.
Okay, thank you, Khaled. Does anyone else have a question for Akalanka? Samuel.
Okay, thank you for the nice presentation. Just a quick question. I wanted to find out. So, for Python, sometimes you make you make library updates, and you are required, due to the version of your new library, you are required to make some changes in your code. So, did you consider that in coming up with the generalized code patterns, or those ones were not factored in, code changes that were due to library updates?
If I understood correct, so one problem with when you use historical information, you always rely on what has happened before. So if the change involve deprecating or replacing a deprecated API just because there's a newer version or better version, then we focused on that, but simply because it is captured by the pattern mining algorithm, and that happened to be found in the same project or in multiple projects. But we cannot really consider it if that did not happen. Does that answer your question? Maybe I did.
Not really. I was okay. So I was thinking in terms of the library. So for instance, the machine learning libraries, for instance, for TensorFlow and the likes, they make the updates, and then it's the code you've written to say for a model, the model code you've written, you're required to refactor the whole code, because once you run it, it's going to break. So I was thinking maybe since you use historic data, so you might the code changes from GitHub. I was thinking that probably you would have included such data, and that's why I was asking if you use that to generalize, like in coming up with the generalized idea, if you use that or not? Because I feel like if you added that, then that one would be an issue going forward.
Yeah,
That was my thinking.
yeah. I mean, now I get it. So that's probably the case, but when we identify generalizable pattern, we try to, I mean, since these are valid commits, right? So because they're coming from the history, so yeah, in a way, we don't really consider whether the commit actually break the code or not. We consider it's like approved because it's actually a valid commit. Then again, yeah, there's a case, as you say, but when you try to identify like generalizable commits, generalizable patterns, we try to see whether it's like more generally applicable, not involved in a particular project. For example, let's just say you've had to replace it just because it is specifically involved to one particular project. So if the change involves an API calls or maybe attributes in that one, we discard them in general as a non-generalizable pattern. So in that way, some of the patterns could be a little bit safer, but at the same time, yeah, what you're saying could happen too.
Okay, all right, thank you.
Mhm. Okay, thank you, Samuel. Diego, please go ahead.
Hey, Akalanka, good to see you. Great presentation, very clear. I remember working on this kind of topic a while ago, and what I like interesting about generalizable code patterns is that they can be used for build linters or recommendations that do not depend on context, right? But then like last year, there came the Copilot, which you can recommend things based on context. So I just wanted you to comment, like if there are some things that you can see that using generalizable code patterns will be able to achieve better than let's say approaches like Copilot, or we're dealing with something completely different here?
Yeah, I'm not sure this is going to compete with Copilot because we basically discard everything that is context dependent. Like for example, that int64. So basically you would be able to recommend if we could identify, okay, if the context actually involve int64, right, then that kind of change pattern could be applied. Like we discard so many of those. Yeah, it's kind of in a way, it's a kind of a drawback because now some of the patterns that identified by the mining algorithm, we discard them just because we don't really know the context.
Mm-hmm.
And again, it's a kind of a tricky thing with Python. It's dynamic, so sometimes you have types coming out of nowhere. So if you don't really know what kind of data types that you're working with, it's really tricky. And also it involves like what kind of a hardware that you're using. Sometimes you feel like, okay, dissolving for loops and using this API is going to be great. But one of the Dilhar and others recent study, when they try to make these commits, they found that in certain cases, like the underlying code that they write for the hardware, that using a loop, it's better than certain APIs because that works really better. So yeah, it's a tricky subject to identify the context, but yeah, maybe something to consider in future.
Right. And just a quick follow-up. One thing that maybe could be considered is that like Stack Overflow, kind of very popular question and answers are related about code, right? Could be a nice, interesting way to find reusable patterns, especially in the answers that are highly voted. That means that you have maybe a solution for a problem that is highly reusable and the community likes a lot. So maybe it could be a data source, an additional data source to incorporate in your catalog of generalizable data code changes.
Yeah, definitely. We use some of the Stack Overflow discussion to understand why the change is necessary when we cannot really find out why it is good. Yeah, so we use it to just to identify the implications, why the change. But yeah, definitely it could be a definitely good addition to find more data.
Yeah, thanks a bunch.
Thank you.
Thanks, Diego. We have about 5 minutes left. Does anyone have any questions for either Akalanka or Pierre-Olivier? Maybe a non-Concordia student. I see there are several students from Queen's and Polytechnique with us. Or just general comments. Or anything from the professors that we have with us today. No, everyone's feeling shy? Or
I
just
don't have any questions, but I just want to say thanks, Akalanka and Pierre-Olivier. These were super interesting. I really liked Akalanka's talk.
Thanks, Ivan.
Yes. Okay, well, if we don't have any further questions, then I'd like to thank both Akalanka and Pierre-Olivier for their engaging talks today, and to everybody for joining this reading week. Our next Trainee Talks will be March 23rd, so make a mental note of that date in your calendars, and I'll be sending more information about the speakers and the topics very soon. So with that, thanks very much, everybody. Have a great rest of your day.
Thank you. Bye-bye.
Bye-bye.
Bye-bye.